Hello and welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be talking about acids and bases. Our aim for today is, how can we describe the properties of acids and bases? Let's talk about some properties of acids. The first property of acid is, acidic compounds give foods a tart or sour taste. For example, vinegar, which is made up of ethanoic acid or acetic acid, imparts a tart taste to a salad dressing, whereas lemons, which contain citric acid, imparts a sour taste. Also, acids react with certain metals, certain active metals, to produce hydrogen gas. And finally, aqueous solutions of acids, so dissolved in water, are electrolytes, which mean they conduct electricity. Here is Table K of your chemistry reference table. Table K has examples of common acids. First you have HCl, which is hydrochloric acid, HNO2, which is nitrous acid, HNO3, which is nitric acid, H2SO3, sulfurous acid, H2SO4, sulfuric acid, H3PO4, phosphoric acid, H2CO3, carbonic acid, you find that in carbonated beverages, and once again we have ethanoic acid, which is either CH3COOH or HC2H3O2. You could use either one. Next we have properties of bases. Bases have a bitter taste, but tasting most bases is hazardous. Most of our cleaning products, for example, are basic. Bases are also slippery to the touch, like soap. Soap both has a bitter taste and is slippery to the touch, but you wouldn't eat soap, of course. Aqueous solutions of bases are also electrolytes, so when dissolved in water, they would also conduct electricity. On table L of your chemistry reference table, you have examples of common bases. The bases are NaOH, which is sodium hydroxide, KOH, which is potassium hydroxide, CaOH2, which is calcium hydroxide, and NH3, which is aqueous ammonia. Now let's talk about how solutions become either acidic or basic. Remember, water, which is H2O, will contain both hydrogen, H+ ions, and hydroxide, OH- ions. For an acidic solution is going to contain more hydrogen ions than hydroxide ions. So for acidic solutions, the concentration of H+ ions will be greater than the concentration of OH- ions. For basic solutions, the opposite is true. So for basic solutions contain more hydroxide ions than hydrogen ions. So in this case, the H+ ion concentration is going to be less than the OH- concentration. Notice I used red marker for acidic solutions because acidic solutions turn litmus, either paper or solution, red, and basic solutions turn litmus paper or solution blue. Red acidic, blue basic. Finally, neutral solutions contain equal concentrations of hydrogen ions and hydroxide ions. So in this case, the H+ ion concentration is going to equal the OH- ion concentration. An example of a neutral substance, a substance that is neither acidic nor basic, is pure water. Pure water contains equal numbers of hydrogen ions, H+ ions, and OH- ions. Remember, water is H2O, and it undergoes a process called self-ionization. So the H2O breaks up into H3O+ and OH-. Another way to write H3O+ would be just H+. Both of these are interchangeable. You can write H3O+ or H+. So water molecules react to form a hydronium ion, that's our H3O+, and a hydroxide ion, that's our OH-. Since the H pluses, or the H3O pluses, and the OH minuses are equal, you have a neutral substance. The symbols H plus and H3O plus can be used interchangeably. Once again, it means the same thing for our purposes. H3O plus and H plus, same thing. The first acid-base model that we will discuss is the Arrhenius model, named after Swedish chemist Svante Arrhenius, this gentleman right here. And he stated that an acid is a substance that contains hydrogen and ionizes to produce hydrogen ions in solution. So it produces H plus ions in aqueous solutions. Whereas a base is a substance that contains a hydroxide group, an OH group, and dissociates to produce hydroxide ions in aqueous solutions. So it dissociates into OH minus ions. Let's take a look at some examples. One example of an Arrhenius acid, and the first acid on chemistry reference table K, is hydrochloric acid. Now first, hydrogen chloride starts off as a gas. When it's dissolved in water, it dissociates, it breaks apart, and ionizes into H plus and Cl minus ions. Now according to Arrhenius' theory of acids and bases, an Arrhenius acid is any substance that, when dissolved in water, dissociates into H plus ions. So this H plus ion makes the solution acidic. An example of an Arrhenius base, and the first base on chemistry reference table L, is sodium hydroxide. Now, sodium hydroxide starts as a solid, and when it's dissolved in water, it dissociates, it breaks apart into Na plus ions and OH minus ions. By breaking up into OH minus ions, according to Arrhenius' theory, this solution is going to be basic. Let's try some practice problems together. Practice problem number 1 states, identify the following substances as either acid, base, or neither. When we look at letter A, HI, hydrogen iodide, aqueous, when that dissolves in water, it dissociates into H plus ions and I minus ions. Since when HI dissociates, it gives off H plus ions, that means that this substance is an Arrhenius acid. When we look at letter C, cesium hydroxide, aqueous, when that dissociates in water, it breaks up into cesium 1 plus ions and OH minus ions. Since cesium hydroxide gives off OH minus ions, in solution, it is considered an Arrhenius base. Finally, lithium fluoride, aqueous, when that dissolves in water, it dissociates into Li plus and F minus. Since I neither get an H plus or an OH minus ion, it is neither an acid or a base. Finally, let's try writing some dissociation equations for Arrhenius acids and bases. Problem number 2 states, write the Ka or Kb equations for the following ionizations. For letter A, HCl plus H2O, that goes to, well, H is going to go with the H2O to make H3O plus, also known as hydronium. What's left over? Well, we have Cl minus left over. Remember, hydronium, H3O plus, is the same as H plus. So having H3O plus in solution, after HCl dissociates, we know that HCl is an acid. And it is hydrochloric acid. If we jump down to letter D, NaOH in water, that is going to dissociate into Na plus and OH minus. Since we have OH minus, which is hydroxide, we know that sodium hydroxide, NaOH, is going to be a base. Finally, let's take a look at letter C. Letter C is H2SO4 plus H2O. When we take one of those H's and bring it to the H2O, we get H3O plus we have HSO4 minus left over. Well, we actually can do that again. We could take another H and give it to another water molecule, which would give us two H3O pluses and SO4 2 minus. Since H2SO4, sulfuric acid, had two H's to give, we call that diprotic. Since H plus, hydrogen, is a proton, because it has no neutrons and no electrons, we say it's a proton, and H2SO4 has two H's to give off, we say it is diprotic, whereas HCl was just monoprotic. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we learned about properties of acids and bases. We took a look at Table K and Table L of your chemistry reference tables. And we also looked at the Arrhenius theory of acids and bases. Remember, an Arrhenius acid is something that gives off an H plus ion in solution. An Arrhenius base is something that gives off an OH minus, a hydroxide ion, in solution. Thank you again for joining us. I hope you learned something today. Please come again soon.